audio equipment here. My name is Jonas, so I can introduce myself first. So I'm a science writer at the moment. So I used to be a researcher in general relativity and cosmology, did my PhD in Stockholm University, and later on moved to Germany and did some dark matter phenomenology there. But nowadays I've shifted career to work as popular science writer, science journalist, and I've been working on a book about black holes. And as a science writer, your goal is kind of more to find science stories. So something in the scientific results that tells us something about our human condition, kind of. And that's what this talk is about today. So the topic is, what do black holes teach us about the Earth? And that might sound a bit weird, like you would imagine that black holes have nothing to do with us on Earth, but there's actually a quite profound story here that's quite interesting. So we're going to talk about that. And oops, there we go. And my journey to write this book about black holes, that started with this image from the Event Horizon Telescope that was released in 2019. When I saw this image, I was really, really impressed that it was possible to produce this kind of image. And I decided that I wanted to write about it and also to kind of explain to a general audience the meaning of the image, not only from a scientific standpoint, but also from a, let's say, a cultural and existential standpoint. And I just to give some background, I just wrote a book contract now and signed a contract. And it was quite funny. I did this just 2 weeks ago. And today you don't write a book contract by signing a piece of paper and having a drink afterwards. You sit by yourself at home and you sign it on a mobile phone, actually. So that was a new experience. And then, is there someone asking questions? No? And then, so what I've been doing for the book is I've been interviewing people. So these are some of the people that I interviewed for the book. We have Shep Dolman, of course, from the EHT, and Roy Kerr, Rainer Weiss, a lot of people. So these are just some of the people that I talked about black holes and how to produce this kind of images and learn more about black holes. I also went and visited telescopes to see at site, to get a first-hand experience of how it's possible to use the telescopes to observe black holes. But what I will talk about today is archival studies. So a different thing. And it concerns this formula, Carl Schwarzschild's famous formula for black holes that was published in January 1916 in an article called On the Gravitational Field of a Mass Point, according to Einstein's theory. This formula is really the starting point for our modern theory of black holes. And a lot of the research that has been done the last 100 years is really about hammering out the consequences of this formula, both on a theoretical level and also on an empirical level. How well does it match up to what we can observe in the universe? And when I read about this formula, about the historical circumstances, there was some quite intriguing statements about it, that Carl Schwarzschild actually found it while being at the Eastern Front in the trenches. So this is a statement that appears in some books. And I thought that was fantastic. Like, wow, he was at the trenches at the Eastern Front in Russia. That's amazing. I want to write about that in my book. But then I read some other statements that he was actually on the Western Front. And I got a bit confused, like, where was he actually? And was he actually fighting in First World War? I mean, what was the actual concrete circumstance where he was when he wrote down this formula and found it? So I got very intrigued by that question to kind of find the truth about that, because there was this contradictory statements in the literature. So what I did was to go to the archive and try to find the truth about that. And what I found there forms the basis of this talk, which is this historical arc, starting with the work of Carl Schwarzschild and today how we use black holes to study the Earth. So let's first recap the historical circumstances here. So I went to this building. So this is the University Archive in Göttingen. This is where the material of Carl Schwarzschild, like the letters and notes and postcards, all of that kind of stuff is stored there in this archive. So I went in there and I said, hello, can I have a look in your archive? And they said, yes, of course, no problem. And this is the material. It looks like this. There's a bunch of green folders, and you just have to dig into that and see what's there, basically. And the first thing I found, one of the first things, was this military identification card. So this was issued in 1915, March. And you can see here that Karl Schwarzschild, you have, for example, he's born in Frankfurt. He's 41 years old when the military card was issued. If you look in the middle, it says Größe, and it says 1 meter, 69 centimeters, so that's his length. And it's a bit funny because the 1 meter is pre-printed, the one there. So they didn't have any people in the army who were taller than 2 meters, apparently. And then below that you can see Beruf, which means his job title, and that is astronom, so astronomer. So then you ask, okay, but he's an astronomer. Karl Schwarzschild is an astronomer. What was he doing in the First World War? So he didn't have to go to join the army. He volunteered because he, for different reasons, his wife later recapitulated that he was, when he grew up, he was from a Jewish origin, and he felt the anti-Semitism in the country. And he thought that if he, as a Jew, would join the army and show that he was like a true patriot, that would increase the respect of the non-Jewish Germans towards him and his peers. So that was one reason, his wife later said. When you read his letters, I think another reason was also that he was very fascinated with the military project, like an adventure kind of thing. But so he joined the army. And when I continue looking around in the archive, I found these notes. So these are notes that he scribbled down in the autumn of 1915 when he tried to solve Einstein's field equations. So Einstein had published these equations in November 1915. And Schwarzschild immediately set out to kind of figure out what was the consequences of these equations. Now, if you look in the upper part of this, or if you look at the lower part, you can see from the mathematical formulas, we recognize them as the Christoffel formula, or symbols, we see the metric coefficients and so on. And so we recognize kind of the symbols immediately. It's the same kind of symbols we use today when we do differential geometry. But if you look at the upper part, you can see his handwriting. And this handwriting is really hard to read. And I had a lot of problems with this. I tried to use this kind of AI technology to read old handwriting, but it was a complete failure, actually. So I was very lucky. I got into contact with Ignatius Adrian Raab, who is one of Germany's foremost experts on the life of Karl Schwarzschild. And he very kindly sent me transcriptions of many of the letters that were in the archive. So he's my main collaborator. I also excuse myself, I forgot to say that in the beginning, but he's one of my main collaborators on this work. And we're writing up a paper where we are describing some of the things that are in the archives that have not been published before concerning the military activities of Karl Schwarzschild during the war. So from this material, so a lot of credit, or most of the credit, should go to Ignatius Adrian Raab for doing the transcription of this very difficult handwriting. So if you look at the letters then you can pinpoint exactly where he was. And that turns out to be quite important. So he was not on the Russian front. He was on the Western Front during the autumn of 1915 in a city called Mulhouse, which at the time was a site of intense conflict during the war. So this is a city that lies on the border between France and Germany and kind of has oscillated a bit back and forth in terms of ownership of this or control of this city. So during the outbreak of the First World War, there was intense battles going on between French and German troops for the control of the city. And the German troops gained the control. So Karl Schwarzschild, when he comes to the city in the autumn of 1915, he writes on the 12th of December, so he has been there for a while, "We are half an hour from Mulhouse, in the very elegant house of the owners and management of a large textile factory. So basically the German troops have occupied a very nice bourgeois building owned by the family of Köchlin, who was a textile manufacturing family in the city of Mulhouse. And that's where Karl Schwarzschild is at this time. That's where he's doing his calculations. And he writes to his wife towards Christmas, I have done calculation on Einstein's gravitational theory and I worked through it. It is really something extraordinary. Here, I always think that if it is right, it is as important as the entire war. So that's quite interesting. So he says immediately that he understands that this new theory of Albert Einstein is extremely important if it's correct. So Schwarzschild is very concerned with working out the consequences of Einstein's new formula. But why? Why was he well equipped to do this? He was an astronomer, and the mathematics that Einstein used, differential geometry on pseudo-Riemannian manifolds, that was very advanced mathematics at the time. So it's kind of equivalent if you would say you would have a new theory like string theory, and an astronomer would immediately, just within a couple of weeks, take that theory, do some very, very advanced calculations, and then produce a result that's astronomically interesting. So it was quite fascinating that Schwarzschild did this so quickly. The reason is that he had actually contemplated that the universe could be non-Euclidean already in the year 1900. He had given a talk to the German Astronomical Society. And he writes, here we are come into a fairy land of geometry. So that's what he calls the non-Euclidean geometry, which is especially beautiful due to the fact that it may relate to our real world. And finally, we are unsure in the impossibility of it. Here we consider how wide the boundaries of this fairy land can be expanded. What is the largest numerical value of the permissible curvature of space? What is the smallest radius of the space curvature? So he was interested in trying to pinpoint if the universe had a non-Euclidean structure very, very early on, which is quite fascinating. And he was a mathematical prodigy. So he was very well equipped, both from a visionary point of view and from a mathematical calculational point of view to do this. And also, but before we go on to the result, I should mention what was he actually doing in the army. That was also calculations. So he was, first of all, doing meteorological calculations, calculating wind, moisture in the air, and so on. And later on, he was doing ballistic calculations. So calculating artillery trajectories and how that was affected by wind, rain, that kind of stuff. So he was doing military calculations for the army, but at the same time, in his free time, he could also do calculations on general relativity. What he found was this. So this is the first time it was the Schwarzschild formula that we call it today was written down and communicated to Albert Einstein towards the end of December 1915. So this is basically it. This is the start of our theory of black holes. Of course, at the time, neither Schwarzschild nor Einstein understood really the implications of this formula. It took a long time, almost 40 years, up until the 1950s, until really the complete consequences, the mathematical consequences of this formula was truly understood. So even though it looks simple, it contains a lot of very advanced concepts. So that's the background. So the answer to the question, where was Karl Schwarzschild when he wrote down this formula, is that he was on the Western Front in the city of Mulhouse. There was intense fighting going on nearby, and Karl Schwarzschild writes about this, saying that he can hear the cannons far away and so on, but he was not himself fighting, and he was not in the trenches. He was in a very nice bourgeois villa with central heating, he also writes. Okay, so that's the backdrop story. Now comes the new stuff. So there was another person present in this villa when Karl Schwarzschild found this formula. So over Christmas 1915, most of his superior commanders had gone away for a holiday break over Christmas. So he was alone in the villa, almost, because there was another person there. And that person is essential for this story that I will tell you about the link between black holes and the Earth. So let's see, who is that? So on the 3rd of January 1916, Schwarzschild writes to his wife, Elsa, "This morning a card came from Einstein, which caused me to first write down the work on his theory of gravitation for printing." So he was doing his calculations, he was preparing to publish his formula, and now he writes, "The loneliness," because he was alone there, "was just starting to get to be too much of a good thing for me when Alfred Wegener, whose brother is the manager of the weather station, appeared, and yesterday we were together for 12 hours. There was again too much to the other side. But he learned to play billiards in Belgium, as I did here, and we had fun with it." So as far as I know, this has not been published before, that actually Alfred Wegener was there in the same villa playing billiards with Carl Schwarzschild while he was doing his final preparations of the article where he published what is now known as the Schwarzschild formula. So who is Alfred Wegener? So he is arguably the most important geologist of the 20th century. So he was also in the war. He was a scientist with very wide interests. He did his PhD under Max Planck. He was interested in astronomy, meteorology, geology, climatology. He did expeditions to Greenland and a lot of things. So he was a very productive and broad-ranging scientist. And he had a theory which he published in 1915. So the same time, same year as Schwarzschild found the formula for black holes. And his theory was that the continents are in fact not at a fixed positions on the surface of the Earth, but that they are changing. So that the continents are moving. So this is the theory of continental drift. And he published this theory, this idea. And of course, this was a very challenging idea to accept because the continents and the surface of the Earth feels very, very stable. So why would you believe that it could move? And this idea was met with a lot of resistance, in particular because Wegener could not produce a physical mechanism that could be the cause of this movement. What he had was indirect evidence. This evidence was primarily deposits. So for example, fossil deposits. When you look at the fossil record, you find that there are fossils that are deposited at the same time, but that today are at widely separated places at different continents. And it's the same with other geological deposits, sedimentary deposits, for example. And this would make sense if these geological deposits were made at a time when the continents were closer together. And also, if you take the continents and kind of move them around like pieces on a puzzle, you see that they actually fit together quite well. For example, if you look at the east coast of South Africa, it fits very well to the west coast, or South America, sorry, it fits very well to the west coast of Africa. So these were kind of the main arguments, studying the geological record and looking at the geographical features of the continents today. And as I said, this was not universally accepted among geologists that this could happen. And in fact, we know that both the theory of black holes, which it wasn't called black holes at the time in the 30s and 40s and 20s and so on, it had different names, but I'll just refer to it as black holes now. So the theory of black holes was also met with resistance, and the theory of continental drift was met with resistance. It was not universally accepted. And in particular, Einstein was very strongly against the idea that black holes could form. So he writes in a paper in 1939, the Schwarzschild singularity does not appear for the reason that matter cannot be concentrated arbitrarily. So this was an argument also produced by people like Arthur Eddington, that it would not make sense that you could squeeze matter into such high densities required to form, for example, stellar mass black holes. And here, Schwarzschild singularity, in this sentence here, Einstein is actually referring to the horizon coordinate singularity, not the physical singularity, the center of the black hole. What's kind of funny is that actually the critique of Wegener's theory meets in the character of Einstein. So he was not only critical of the theory of black holes, but he actually wrote one of the last texts that Einstein wrote was a foreword to a book by Charles Hapgood that was published in the 50s called Earth's Shifting Crust. This book is basically an attack on Wegener's theory. And Hapgood had an idea that many of the geological features we see today are due to sudden disruptions and stresses in the crust of the Earth. So this is called the crust displacement theory. And Einstein wrote a foreword to this theory and kind of said that, well, this might be a reasonable idea. This theory is highly proven to be false today, but it actually reappeared a few years ago. It's kind of funny in the movie 2012, this apocalyptic movie where they make explicit reference to Hapgood's theory. And that this crust displacement is actually the cause of this apocalyptic scenario that occurs in this movie. Now, so there was a common critique against the theory of black holes and continental drift, but there was also a commonality in when the first empirical evidence started to appear for these two theories. And that happened in the 60s. First of all, it was the work of Harry Hess, who was he was an admiral during the Second World War, was out at sea with battleships. And after the war, he started using sonar mapping of the ocean floor to study the structure of the ocean floor. And he published a paper here in 1962, History of the Ocean Basins, where he showed that actually there is a lot of structure to the ocean floor. There are these ridges where new matter seems to be formed. So these red lines here are, the color coding here is in terms of time. So the red lines are new matter being formed. And then there are other places where old matter seems to submerge and disappear. So what Hess proposed was that what is going on here is that the surface of the Earth is segmented into tectonic plates. And new matter is swelling up along these ridges, and the tectonic plates are subdued under their neighboring tectonic plates and go down into the Earth. And because of this, the tectonic plates are moving, and in turn, that means that continents are also moving. The cause of this is convection due to thermal gradients within the Earth, and also gravity that is pulling these more some of the cold, low density parts of the tectonic plates down. And so Harry Hess could supply a physical mechanism that Wegener could not supply, and gravity was a chief component of that. At the same time, we also have, or 1 year after this, we have the publication of Martin Schmidt of the identification of the object 3C273, the first quasar. So this is an object that looks like a star in the sky, so like a normal star. But when Schmidt and other astronomers, they studied the spectrum of this object, they discovered that it had a very large redshift. So it has to be very, very far away in the universe. But that means that if it is very far away in the universe, but looks star-like here for us on Earth, it must have a very, very high light output, a very high luminosity. So, and when they also studied the brightness fluctuations in this luminosity due to the time period of these fluctuations, they could also see that this luminosity must be created from a very, very small volume. So something contained in a small volume is producing a luminosity that could be seen across the universe, which is very fascinating. And one of the proposed mechanisms for that was black holes. So the deep gravitational potentials of black holes could convert infalling matter, the energy of that, somehow into the production of this very, very large luminosity. The same was also seen in the galaxy, in our Milky Way, the study of X-ray radiation from Cygnus X1 in 1964. We have where it was proposed that it was a stellar mass black hole that produced this high degree of X-ray luminosity as accreting matter was falling into the black hole. So very, very quickly, we get evidence. In the case of the tectonic plate movements, that's quite strong evidence. In the case of the black holes, it's more tentative evidence. This isn't a direct proof. But we see that in both cases, looking deep down into the ocean and far out into the heavens, we see gravity at play. So it's gravity that's causing the movement of these continental plates together with the thermal convection cells. And it's gravity that produces these high luminosities, both from extragalactic objects and within our own galaxy. Now, so there's a commonality here, but that doesn't mean that this is the same thing, of course. But there's a commonality in the scientific trajectory in terms of acceptance of these two ideas. And this was pointed out by Werner Israel, who was a prominent black hole theorist working with Stephen Hawking and so on. So he writes a very interesting paper in 1996 saying that he asks the question, why was there this commonality in the critique of these two theories? And he proposes a psychological explanation. He says that the reluctance among geologists to consider drift seriously was instinctive and emotional rather than factual. Having just learned to live with the abyss of time, they were not yet prepared to deal with the uncertainty of place that is inherent in a world of drifting continents. It's a very beautiful statement. And then he connects this also to the theory of black holes. And he says that each, so both the theory of continental drift and the theory of black holes, threatened man's instinctive faith in the permanence of matter. It's quite strong statements, and he's basically doing some kind of psychoanalysis here of why there was this reluctance to accept these two theories. But as far as I know, he wasn't aware of the link with Wegener, which I think he would have liked that. And of course, he wasn't aware of what happened next, which is the incredible thing. And that's when you actually join the study of the Earth with the study of black holes. So what's going on there? Okay, let's go back to this picture. So this was published in 2019. So it's an iconic picture. It's an amazing picture. And how is it produced? Well, as most of you know, and I mean, many in the audience here was involved in this, this image was produced by, you need a telescope the size of the Earth, which is not possible. So you use this technique of very long baseline interferometry, where you take telescopes located at different sites, at different continents, and basically it's these distances between the telescopes, these baselines that form your fundamental observing unit. And as the Earth rotates, you trace out different baselines, which in turn trace out different Fourier modes in the image that you want to produce. That's the technique you're using. And what's so amazing about this is, of course, that the Earth itself is a part of the telescope. You use the rotation of the Earth to trace out these baselines. But in order to manage to do this, you need a high degree of control of your spatial precision and also your temporal resolution of the data that you're recording. And the spatial precision, you need to know the position of the telescopes with a millimeter accuracy in order to do the correlation analysis of the data that the telescopes are recording. So what this means is that you actually have to take continental drift into account, because that happens on the order of tens of millimeters. So continental drift, to understand that, to measure that and have control of it, control of how big it is something you need to know about when you do these black holes observations. But that also means that you could switch the situation. Maybe you could observe black holes, let's say quasars, which have a fixed position in the sky, in order to learn more about continental drift. So this was pointed out, for example, Heino Falke, who's been involved with the Event Horizon Telescope from the beginning, says that it isn't just astronomers who use continental interferometry to measure the heavens. Geodesists also use VLBI telescopes to survey and measure the globe. So what does that mean? Well, so I went to the west coast of Sweden, to see how that is done. So this is the On-Solar Space Observatory. It's a geostation. It's this space observatory is a facility that is used to do measurements to improve our understanding of the Earth. And one thing they do there is space geodesy. So what is that? First of all, this place is beautiful. If you ever get the chance to go to Sweden and visit some telescopes, go there, because you see how nice it is. You have like the elements meeting here, the sky, the sea, the rocks, and the space through these telescopes. So what these telescopes are doing is that they are observing quasars. So quasars are these objects, celestial objects or celestial phenomena produced by supermassive black holes. As matter is falling into these black holes, there's this immense luminosity output that can be seen across the universe. When it comes here to the Earth, it's quite weak. So what you do is that you join forces with other telescopes to observe these quasars. So you have a whole array of these VLBI measurement stations that observe different quasars and then do a correlation analysis of the data, interferometric analysis of the data, to pinpoint the position of the quasars. What happens is that you get a map of the quasars in the sky. This map is called the International Celestial Reference Frame. So that's a map that you kind of use in the same sense that you, back in the early days of navigation, you had star maps. So suppose you wanted to navigate across the desert or navigate across the sea with ships, you use the stars for navigation to pinpoint your position. But today, if we measure the stars, I mean, they are moving, we can measure that movement with the aid of, like, the Gaia satellite, for example, measures that the velocity of the stars to extremely high precision. So they are not really at a fixed position for our purposes in the sky. So you need something that's even further away, and quasars provide these fixed reference points in the sky. So this network of stations, of telescope stations, they, with the aid of their observations, you can create this kind of celestial map. Then you can use that in turn to create this kind of map. So this is the global terrestrial reference frame. So you go from the celestial reference frame of the sky to the terrestrial reference frame of the Earth. So by observing these quasars, you can pinpoint the position of the telescope and calculate or deduce how it's changing with time. So if you're looking at the lower left part here in this map, on this legend, you see that the first arrow, the brown arrow there, corresponds to GPS, and the second arrow corresponds to VLBI. And then if you look at the map, you can see many of these red arrows here indicating the movement of the continents. So that's actually the movement of the telescopes are moving in this way. And from that, you can then deduce that, well, then the continents that they are standing on, or the ground that they are standing on, must also move in this way. And you can use these measurements for a lot of different purposes, not only continental movement, you can also observe the altitude movement. You also have attenuations of the signal, of the radio signal in the atmosphere. So you can use it for atmospheric studies. So there's a lot of different things that you can use with the aid of these quasar measurements. In particular, I want to highlight how you use the quasar VLBI measurements as calibration tools for our other systems. So in particular, look at the upper right part here. You have the GNSS satellites. That's a global navigation satellite system, GNSS. So the foremost example of that is the GPS that we use every day. So GPS is the American version of the GNSS, but you also have a European version, Russian version, Chinese version with their own satellite systems. But they provide spatial coordinates for us here on Earth. Problem is that today you want really high degree of accuracy, and the Earth is rotating. We have a gravitational tug on the satellites. The rotation of the Earth is changing a little bit with time. So there's a lot of things going on actually when you want to do precision measurements of the Earth, of spatial positions on the Earth. And then you use these VLBI quasar measurements as calibration tools for this GNSS system. So when I was at the west coast of Sweden and visited this Onsala Space Observatory, this geostation, I asked the professor Rüdiger Haas there, who is doing this kind of analysis, I asked him directly, like, can you really say that when we use GPS, that we are actually using black holes to navigate on the surface of the Earth, thanks to this calibration? And you know, if you ask a politician, you want a direct answer, then it can be hard to get a yes or no. But in this case, when you ask this space geodesist, he immediately said, yes, this is correct. So every time you use a mobile phone to navigate, say with Google Maps and GPS, you're indirectly using black holes to find your way on the surface of the Earth, thanks to the calibration of the GPS system with the aid of VLBI measurements of quasars. So that's quite fascinating. So black holes actually play a role for us today when we navigate on the surface of the Earth and for our study and understanding of the Earth. Because the next step of this is, so Rüdiger Haas also wrote an article here in Nature 1 year ago called Clock Comparison Using Black Holes. The next step in this is that you actually want to compare optical clocks at different continents. So today we have extremely high precision optical clocks, but we know that they can drift with respect to each other. So maybe they drift because of construction problems. I mean, could happen, but also they could drift because we have shifting gravitational potentials at different places on the surface of the Earth. So what you want to do is really get a high degree of control of your relative position of your optical clocks when they are situated at different parts of the Earth. And what Rüdiger Haas analyzed here is a proposal to use these VLBI quasar measurements to check the relative precision of optical clocks at different places, at different continents. And what this leads to, he writes, is this work opens the door for a potential further development of classical physical geodesy towards advanced relativistic geodesy. So this is the final conclusion then, that what is classical physical geodesy? Well, that's understanding spatial relations on the surface of the Earth. What is relativistic, advanced relativistic geodesy? Well, that's the lesson of Einstein, that it's not only about space, but also about time, because we know that different gravitational potentials will cause relative shifts in the clock rate, in the rate of clocks, how they tick. And that is due to, for example, the interior density profile of the Earth. So by using these VLBI quasar measurements, you can get a better precision of not only spatial relations on Earth, but also the entire space-time continuum around the Earth, which is really amazing. So black holes in the future can aid us to map out the space-time continuum around the Earth. So let me end with that, so we have time for some discussion and comments. That going back then to this original meeting between Schwarzschild and Wegener in this villa in Mulhouse, 1915, winter of 1915. So imagine that you were there. I mean, would you have imagined that when Schwarzschild found this formula, that 100 years later, there would actually be a meeting of these two theories, the theory of the black holes and the theory of continental drift, not only in the world of ideas, but also in the world of practical technological application. So that's the talk, and that's the conclusion. So this is what we learn about black holes. They teach us about the surface of the Earth and how that is changing. So thank you. And if you want to follow me somewhere and contact me, you can do it here on these places. Yeah, that's it. Any questions, comments?
I have a question.
Yeah.
Okay, Peter.
I have a suggestion and a question. My suggestion is that the history of continental drift is actually one of the better studied episodes in the history of Earth sciences. And either the work of Naomi Oreskes comes to mind, who's written books on this, edited volumes on this, and comes to a rather different assessment about why continental drift was and wasn't accepted, having to do with the sort of epistemic standards, the difference between morphological and physical measurement in Vine Matthews, ocean striping measurements, and so on. So my suggestion is that you make use of the exceedingly good history of science, which I don't say as a partisan to history of science. There's plenty of parts of history of science that I don't think are well understood, well studied, but this is. So I think that would actually be quite interesting for you and would allow a deepening of the understanding of what Wegener was up to in this, exactly in this period, all the way up to and including the 1950s, when it was really accepted. The question is, with GPS is of course one of our go-to arguments for why we should, if you want to convince somebody that general relativity is, or special relativity is valid, you say, turn on your navigation, it would stop working in a matter of minutes. You would not get on the right road if general relativity and special relativity were not built into the system. And so my question is, because I'd love to use the example of black holes in this respect, how much of a difference does the correction to GPS take quantitatively as a result of correction against VLBI assessment of the positions of the cosmic map, or whatever they called it, the absolute reference frame?
Yeah, that's a very good question. So first of all, thanks for the comment about the reference. So this is a work in progress. So it's excellent to hear about different ideas and references I should check out. As for the exact value, I don't know that. So that's something, for example, now let's see here, I'm going in the wrong direction. That's something Rüdiger Haas could explain, and I could get the numbers on that. But I think probably not for like daily applications, like when you use Google Maps. I think the GPS system works perfectly fine. But when you want to do more precision measurements, then I guess that you need this kind of calibration.
I've been told, I've heard this argued when I was writing Einstein's clocks, Poincaré's maps, but one account is that when they launched the first GPS satellite, some of the Air Force physicists did not want to wire in the general relativistic correction. And so they set it on a controllable switch, and they saw that when they didn't turn it on, they got the wrong results, and when they did turn it on, they got the right results. I don't stake my life on this because I heard different things from some very prominent physicists who were involved with this episode, but it's got a 50% likelihood of being true.
Yeah, I remember this story. I tried to track it down also, the source, and it was a bit unclear. But it is floating around there, yeah. But it's a very fascinating story, definitely.
Eric?
So thank you. That was that was really interesting. I have two short remarks, which are somewhat pedantic, but the inner pedant in me will not be denied. And then I have a question. So the first remark is that you were ambiguous when you were discussing Schwarzschild's notes to himself in his letter to Einstein and the published paper, and the form of the metric that he wrote down. So there's a very interesting subtlety here. Formally, if you just look at the syntax, the symbols, it's what we today call the Schwarzschild metric. But there's a subtlety. It's not the Schwarzschild coordinates, what we today call the Schwarzschild coordinates. So it's actually really not what we call the Schwarzschild metric. You have to do a coordinate transformation, which will take you from that big R to that little r, which will and rewrite it that way. That will actually give you what we today call the Schwarzschild metric and the Schwarzschild coordinates. So and then the other thing was when you were talking about Schwarzschild's 1900 talk, I think it's important to to emphasize that he was talking there about the curvature of three-dimensional space, not anything like curvature of a four-dimensional space-time. So those are my pedantic.
Yeah, no, excellent. I mean, I completely agree. So that's one step when I show this slide that I jump over, because I mean, you're perfectly right. Like, you have this equation up here also with the capital R relating to the coordinate small r. And just to reiterate what you said, it is really fascinating that this coordinate system, it basically stops on the horizon. So you won't reach the interior Schwarzschild solution. And if I'm correct, that was the complete, what we today call the Schwarzschild solution, should actually be called the Schwarzschild-Droste or Drost solution. So it was this Dutch mathematician and physicist who wrote down the complete solution that also covers the interior part of the black hole.
If I remember correctly, Eddington also came up with it independently, but I'm not a historian, so I think I would bet one beer on that, but I would not bet two.
Yeah, absolutely. And this part, I completely agree too. Like, this is about the spatial curvature, definitely. So, but it shows that he was aware of this question of the non-Euclidean geometry. Yeah.
So my question is about the really fascinating, kind of very complex evidential network that you're pointing to between the use of quasar quasar measurement by VLBI to measure continental drift, and the fact that we have to take continental drift into account in making these VLBI measurements of quasars. Do you know when was it first realized that that continental drift had to be taken into account in order to make the quasar measurements? When was it first realized that? When did astronomers first realize that they had to start talking to the geologists? And when did and how was it realized that you could you could achieve a kind of jiu-jitsu move and reverse the situation and actually use the data in the opposite evidential direction? This seems to me like a really extraordinarily complex and interesting kind of evidential network.
Yeah, that's very true.
How was it all worked out?
Yeah. I'm not sure about the exact time when that was realized. When you do that, it was a very good expression, the jiu-jitsu move. Is there maybe someone in the audience who's more of an expert on the VLBI history?
Yeah, actually, a lot of it was done at the CFA. It was Erwin Shapiro's group, Shapiro of Shapiro Delay, who is also a radio astronomer, VLBI, etc. So his group actually did a lot of the, I think, important geodesy-related VLBI work. Exactly when they started, I don't know. But my guess is it would have been 70s or, middle 80s, something like that. It was going on for a while. I don't know what the current activity is.
And you could ask him, Shapiro. He's around.
Yeah, you should ask him.
Yeah.
And Rebecca Chabonneau, who gave a talk a few weeks ago, was talking about another, place that the connection between VLBI and geodesy came up in the midst of the Cold War, doing VLBI across the US and Russia. So she's probably another person who might have interesting things to say about that connection.
Yeah. And I think also she mentioned in her talk that the first VLBI experiment was done with Onsala Space Observatory and the US astronomers, or VLBI people. So Eric, do you have any comment on the answers?
No, I would really love to learn the details, because I've been thinking a lot in the past year or so about evidence and how complex evidence is and how it works. And this just sounds to me like a really fantastic case study to really try and dig your teeth into. But no, I would love to learn more about it. Jamie, can I ask a quick follow-up, or is there
There's another question from Ramesh.
Yeah, which is actually same topic. I should know the answer, but I don't. So my understanding is that most of this application of VLBI to geodesy was done at centimeter wavelengths. These are the traditional radio frequencies. I don't know how high they went in frequency, But one of the big achievements of the EHT was to push Earth baseline VLBI all the way to 230 gigahertz, 1.3 millimeters. And that was really tough, and it was a great achievement. What I wonder is whether that shift has percolated back to geodesy and whether it has, allowed even more precise measurements. That part I don't know. Wondering if you had any information on that.
I don't know that, but that's a great thing to investigate for sure, to see if there's been an improvement. But I don't think that that's what I'm unsure of, how many of
They
these
don't have
networks.
230. That all those places don't have 230.
No, they don't. But the ones
Exactly.
they do sit on different continents.
Yeah.
So, yeah.
Yeah. So I'm unsure if these networks could use the improvement that the EHT came up with. Yeah. So Camille, or another comments, or should I answer the question in the chat?
Yeah, if there's a question in the chat, then I think
Yeah, the question was if there was any evidence that Schwarzschild discussed his work with Wegener. So there is evidence in the letters that that Schwarzschild discussed Wegener's work. So there are statements that he heard about the theories that he thought was very far out, kind of. But I haven't found anything that they discussed Schwarzschild work. But it wouldn't, it's not unreasonable to imagine that they were doing it, but there's no evidence of that, as far as I know. And I also want to comment one thing on Peter's statement here, that if we look at Werner Israel, so this statement, there are also other statements by him. He basically says that the evidence for both continental drift and black holes was overwhelming in 1916. So that's a statement that appears in Kip Thorne's book, for example. And that's one of those statements that I found very hard to believe. In 1916, there wasn't overwhelming evidence for black holes, and the evidence for continental drift was indirect. So I think these statements by Werner Israel are very good for trying to understand the psychological framework, but I'm not sure about some of the statements. I feel are a bit too strong. Yes.
Eric?
Thanks. So I now have one remark to make about that. I'm truly shocked to hear that Israel said that. Because Israel I think in the 1979 collection he co-edited with Hawking, he wrote this really lovely piece called Dark Star, The History of an Idea, or something like that. And he actually gave I thought, very sensitive discussion of the history of the development of the concept of a black hole. So it actually, I find it really shocking that he would make such to my mind, just flat out wrong statement.
I'm shocked about that too. So, and I tried to, if I remember correctly, the source is in Kip Thorne's book, and it's like private communication or something like this. So yeah.
Anyway, my question is about the graph you showed that had where you it had the little arrows that if I interpreted the graph correctly, were showing measurements of continental drift from different measurement sources. Yes, that one exactly.
Yeah.
And I'm just curious. So at least on some of them, it looks like there's fairly significant disagreement on the drift measured by the GPS and by VLBI. Do you know is it known what the sources of error are, or the sources of discrepancy?
You mean, for example, on the West Coast here, or?
Yeah, well, or so right in between South Africa, South America, and Africa, kind of right in the middle of the Southern Atlantic. There's one with very divergent arrows. There's some with very divergent arrows at the tip of South America. Yeah, on the west coast of North America. It seemed to the southeast of Australia, down below New Zealand.
I'm not sure. That's my honest answer. I'm not sure. So some of these details about VLBI and some of these details about the continental rift, I'm not really an expert on, so that I can't answer that, unfortunately.
I mean, Eric, it could be that what you're seeing is the errors that are induced by using GPS without correcting for what happens to the satellites.
Mhm.
I mean, because what VLBI is doing is measuring that against the quasar frame. I don't know what its official name is, but you know, so it could be that, you know, there are effects, orbital effects, that are things that are happening to the relationship between the orbits and the complicated motions of the Earth. You know,
Can I ask what the other, so we've got the GPS and VLBI, what are the other two?
So I think this one, SLR, is satellite laser ranging, and DORIS is another system where you have satellites that are receiving signals from stations on the Earth instead of sending out signals like the GPS system is doing. So there are other techniques for mapping spatial relations. Yeah, but Peter, yeah, that could be one explanation, but it's definitely something to try to understand better. I will look into it.
Thank you.
nice talk.
Yeah,
Thank you,
this
Jonas.
is such a fascinating story.
It's a lot to learn, a lot to think about. Yeah.
We should probably end there because we have, you know, a minute or two until Julius has to give a talk. He's raising his hands like, I don't need to talk.
Okay, great.
But the link for Julius's talk is in the chat for anyone who's interested. Thank you so much, Jonas. This has been really fascinating, really interesting history there.
Yeah, thanks for.
Jamie, you said the link was in for Ulysses Talks in the chat. I don't see it.
Oh, you must have joined just after I put it. I'll paste it there again.
Thanks.
There we go. Okay. Bye, everyone.
Great. Thanks. Bye, everyone.